having discussed a little about Newtonian and non-Newtonian behavior of the fluid and some other relevant items, we come to now the actual nitty-gritty of derivation of Navier-Stokes equation for incompressible isothermal fluid flow. So remember that when we make that kind of statement, there are inbuilt conditions and assumptions that we are imposing on the fluid flow. That means that whatever we do later on will be applied to a fluid flow motion only under these conditions. So if these conditions are broken or changed, then these equations that we develop will not apply to them. We have to go for some other equation. So remember this kind of thing, that it is very important that what kind of conditions we are taking into consideration. So when it is incompressible, then it means that during the flow time of the fluid, the density is not going to change. It will remain constant, and that is why it is incompressible. In compressible fluids, the density will be changing with time or with the other pressure or with the fluid flow pressures. So incompressibility is an important factor, and therefore in such case rho will be constant. And similarly, it will also imply that the viscosity, the relationship that is between the fluid flow and viscosity, also remains the same. The viscosity of the fluid does not change. So this is also an important consideration, because if in a fluid flow motion the density changes, the viscosity changes, the equations of motion will become very complicated, and that will make them very difficult to solve. Already there is enough complication because of the non-linearity that exists in the equations. And if we allow rho and mu to be changed, nu is kinematic viscosity is mu over rho. So that thing is known as kinematic viscosity, or if you take only mu into consideration, then that is the coefficient of viscosity. The viscous stress tensor that we have mentioned earlier in Cauchys equation, then in this one, the relation between the strain rate and the stress tensor is that tau is equal to 2 times mu into epsilon ij, where epsilon ij is the strain rate tensor. So epsilon is indicating the stress rate tensor, which has theoretically 9 components, and when fluid is at rest, it restricts itself only to pressure, but otherwise there are other components that are coming into it. And the equation here, it shows that stress is linearly proportional to strain in Cartesian coordinates. So therefore there are 9 components that I showed earlier and we discussed, and in which you will recall, we had separated the pressure terms and those terms. However, these terms here, tau ij, in the tensor, the 9 components are indicated as tau xx, tau xy, tau xz, and so on. And if I write them in the expanded form, then they can be written as 2 mu du by dx, and when I say du by dx, this is the partial derivative. And remember, the epsilon ij is related to this form, and that is why it appears as 2 mu here, because here I and j are the same. So this is 1, 1. And that is why there will be two such components. Partial derivative of u by x plus another mu times partial derivative of u by x. And the similarity you see in other terms as well. And the remaining terms are shown as indicated. This we write in this form as well. We know that the stress tensor sigma ij is the sum of these terms that I showed you earlier also. These are the pressure terms and these are the strain tensor terms. So when we separate them, we can write the stress tensor as pressure, and this applies when the fluid at motion, plus strain tensor, which has these 9 components. The totality gives us the stress tensor values at respective components. Now we substitute these 3 Cartesian components in the Cauchys equation, and for convenience, if we consider only these components in one direction, x or y or z, then they will all be similar in nature, they will all be similar in their behavior. So it is enough that we consider one direction, and then from that similarity and symmetry, we can sum up all the terms and put them together. So these terms, if I write them, will be rho into du by dt, because u here you see, because we are considering only in the x direction. dp by d, partial derivative of x, this is taken from gradient of p, and we are taking its x direction. So therefore we have dp by dx. Similarly for gravity, we write in generality rho gx. You will recall I mentioned that although gravity always acts in downward direction, so it may not have any contribution to make in the x direction if it is horizontal, but it's not necessarily so always, and therefore in generality we have to put down these conditions. And similarly, these are the other terms that comes from the strain tensor. And we have already mentioned that the pressure is the normal stress only, and it contributes only one term to this equation, and that term is written here as dp by dx. And also if we note that really the partial derivatives that occur, we may be differentiating partially some component of velocity first with respect to x and then with respect to z or y. If we interchange them, then the order of this differentiation does not really matter, because this term in the end will be written as d2w by dx into dz, and you know that the end result will be the same. So therefore we conclude that the order of this partial differentiation is really irrelevant, and we don't give much importance to that. And then after some rearrangement of the viscous terms, we reduce our above equation, that is the forces acting in the x direction, reduced to this form, which can be written as you see here. And why we have written it in this form? Because for our convenience, look at this term and look at this term. The term seems to be familiar. This one is divergence of v. You can see the components u, v, x, and these ones appears to be del, which is del of u. And so for simplicity, we can write this equation as dp by dx plus rho gx component plus rho d by dx of divergence of V plus del square of U, and you can see then we can simplify. This term is continuity equation and it can be reduced to 0. And when we write down, we can write the same equation in this form. As you have seen here, if this term reduced to 0, then this whole term will be reduced to 0. And therefore, we are only the non-zero term that appear from here is this. And so, our equation reduces to this equation. And when we try to write down the same, this was in the x component. If I try to write down the same equation, the same terms, in the v and w direction, I will obtain these equations. You can see they are very similar in nature, very symmetric, and almost the same thing. I can combine them all, put them together, and by putting them together, the answer will be this, which is really the Navier-Stokes equation for incompressible fluid flow. A very important form, and sometimes this is also written as dV by dt plus 1 over rho into all these three terms that are there. So these terms are written, this is known as Navier-Stokes equation, the all-important equations for considering the fluid flow motion. And you can see the component-wise, if I have to write, I write it in this form. The Laplacian, the del square, sometime we call it, is equivalent to that. And in cylindrical polar coordinates, it can be written in this form. So these are the components of Navier-Stokes equations.